whole shebang. Oh, okay, thank you. Right, can I get rid of that? Or will it just go in time?
Should go in time.
Good, okay. Right, well, here we've got Dave Tyler set up. So we've got a nice refractor, and of course he's got his H-alpha kit on here, blocking filter on the back, and energy rejection filter on the front. But he's also got a custom-made, I think it looks like a Coronado probably there, strapped on the side as well, piggybacked on, which is fantastic. And that's my setup. And it's a Coronado Neostar 70mm, and I've had that now for about 20 years. Cost I think just over £2 grand, so it seemed like a fortune at the time. But when you think that I've been using it now for 20 years, just about every day the sun's available, it's pretty good value for money. So it's like everything else when you invest, you know, in a piece of equipment like this. It might be pricey, but you know, it reduces cost during time, and it's certainly well worth it. I mean, it doesn't wear out or anything, so it's well worth an investment, because what you see through one of these is absolutely phenomenal. First time I looked through one, well, that was it. I had to go and have one. It was that impressive. So you'll be familiar with the basic composition of the sun and the nuclear core, the radiative zone, convection zone, and then the photosphere where sunspots are observed. Above that, we have the lower chromosphere where temperatures are about 4,000 degrees centigrade, and then the upper chromosphere where temperatures rise to about 10,000 degrees. Then we've got, of course, the corona where temperatures soar to in excess of 1,000,000 degrees. The mechanism leading to the heating of the corona is not yet understood fully, and it's thought that magnetic tornadoes funnel their way up into the corona from the upper chromosphere, somehow converting their magnetic energy into heating the corona to over 1,000,000 degrees. Can you still see that pop up? Because I can.
Yeah.
Yeah, can we get rid of that at all? That's going to be a big nuisance.
Which pop-up?
Click on it, certainly.
It says this meeting is being recorded.
Oh,
Yeah, just click on it.
just click on it.
Click on it, it will go.
Oh, good. Okay, that's great. Thank heavens I got rid of that. Right. Okay, so we've got two probes then currently on the way to the sun. We've got the Parker Solar Probe and ESA's Solar Orbiter. So we'll have a look at the Parker Solar Probe first. So that was launched 2018, a 7-year mission to the sun. Its closest approach was in January this year when it came up to 13.5 million kilometers. But it's really the last 5 orbits being in, and they should occur around 2024, towards the end of 2024 and 2025. And it's going to fly within 3.8 million miles of the solar surface. And when you think the corona extends about 5 million miles from the solar surface, you can see that this probe is going to be over 1,000,000 miles into the corona itself. That's going to be quite startling. It's going to have fantastic temperatures to put up with, over 1,000 degrees, well over 1,000 degrees. So I hope it's well protected. I'm sure they've taken a lot into consideration, and I hope it doesn't melt when it gets to its target position. We'll have to wait and see. So that's what it's going to do. It takes all these slingshots around Venus, and it gets itself closer and closer to the sun with every orbit. And I've got a little animation there, which will just show you what it's going to do. We're going up to 2024, and it's those final 5 that will be really interesting. They're the ones we really want to see. At the same time, we've got the ESA Solar Orbiter on its way, and that's it's going to sample the heliosphere, or the solar wind. So it's not going to go anything like as close as the other one. However, these are the 2 closest probes we've ever had towards the sun. So if we didn't have the Parker Solar Probe, this would have been the closest one ever to have been sent to the sun. So it's going to do some high latitude observations. It's operational from next year for about 5 years. And it's still going to get pretty close. I think it comes to within about 30 million miles, which when you consider the sun, that's pretty close. That's a distance of over 90 million miles. So pretty good. So doing some routine science at the moment. It's going to fly over the poles, as I say. It's going to measure the solar wind. It should give us hopefully some clues about coronal heating, and maybe some ideas as to what drives the 11-year cycle, because we still haven't got that pinned down yet either. Right, I'll move on to coronal holes, and we'll start looking at the main features then on the sun. Coronal holes, these are the dark areas that you can see there. This is a picture from the SDO, Solar Dynamics Observatory, and it's being imaged there in extreme ultraviolet light. Through these dark regions, these dark coronal holes, that's where the fast solar wind escapes. It's an open magnetic field line structure, so it's a sort of cooler and less dense than the surrounding plasma. That's obviously relative. More prevalent solar minimum, but they can appear at any time. These holes are more stable at the poles, but they can work their way down to the equatorial regions. And when they do, due to the sort of faster rotation of the solar at the solar equator or at those regions, then these holes are more likely to produce more powerful particles when they reach the Earth. So if you've got coronal holes opening up anywhere near the solar equator, they're more likely to result in a powerful aurora. So there's a variety of features that I'll just run through these first, and then before I get on to the next one. So we do have the fast solar wind areas there, of course, are active regions, the dark regions that we're looking at for coronal holes. And then we've got the low speed wind, which is continuously coming out of the sun as well, caused by solar streamers. Right, let's move on then to the chromospheric features themselves. So there's a variety of new features that can be observed in H-alpha. So if you've only previously had a look at the sun in white light and noticed sunspots and faculae, then you've got a whole world of entertainment coming up if you look through an H-alpha scope. So let's have a look in more detail at some of those features, which will certainly enhance your observing experience. So the first one is plage. And you can see those sort of bright areas there in the solar chromosphere. So that is your plage. And these basically are bright patches or areas of enhanced temperature. And they're found mainly near to active regions. Although plage can appear anywhere in the sunspot latitudes, and they often herald the emergence of an active region or remain after it's decayed. So it's a good sort of signature if you see some plage rotating around the eastern limb, and you can expect maybe to see an active region develop there if there isn't one there at the moment. And similarly, as one dissolves on the disk, then the plage usually remains for a while. So plage is sort of similar to that of faculae in white light, although it is a different feature, and the relationship isn't quite understood either. So we can have a white light feature of faculae, which again heralds sunspots and remains after they dissolve. And then in the chromosphere or the solar atmosphere, we have plage doing much the same sort of thing. So plage, well, it contains emerging magnetic flux tubes and reconnecting magnetic field lines, leading to a release of energy and higher temperatures. Plage often surrounds a sunspot group in a cloud-like formation, but as the sunspot grows, and if it's bipolar, the plage divides between the leader and the follower sunspots along the group's neutral line, where polarity reverses. And when a sunspot decays, the neutral line becomes blurred with time and eventually dissipates. And you can see an example of that there. So we've got a bipolar sunspot. So what you've got is, say the leader is positive and the follower negative. Then somewhere down the center here is the neutral line where polarity reverses. And that's where you're going to get magnetic connection and reconnection. And where you get that going on, then that's a hotbed for solar flares. So it's somewhere to keep an eye on. Again, in this image, you can see that quite clearly. So sunspot, trailing sunspots, and again, you can see you've got some pretty bright plage there, if not a solar flare emerging right along that neutral line. Also, you can get filaments also lying right along that neutral line as well. So again, that's something to look out for too, because again, you can get flares associated with filaments too. Okay, if we move on to spicules then, and these spicules, they are hot, the jets of hot gas and move vertically at speeds around 50,000 kilometers per hour, but they're very short-lived, only about 10 minutes duration. They're best seen along the solar limb against the dark background of space as an emission feature. You can see them along there. Not this is a prominence half, but it's this kind of bright sort of furry appearance along here. So not only do we see them along the limb, these little sort of bright emission spicules here, but you also see them right across the solar disk as well. And when you're seen across the solar disk, they're seen as an absorption feature rather than an emission feature. So they're then referred to maybe as a sort of dark mottling effect that you see across the solar disk. They're only about 10,000 kilometers high and 300 kilometers in diameter. They're larger at the poles, but not a lot. They're rarely over 10 arcseconds, and that's why within the solar section, we'll say, well, if you're going to send in an observation over prominence, then we'll make sure that that prominence is in excess of 10 arcseconds in height, just to distinguish it between prominence and spicules. And there you can see in this rather lovely tile, I've got a really nice filament, but look at all those spicules in the background there, just to prove to you that they are all over the solar disk. And there you can see them as those absorption features or mottling. And in this image as well, you can see them really clearly out here, so all around there. And then you've got the sunspot here, which is a strong magnetic area. And you can see something is starting to happen to those spicules around that, which brings us on to the next feature, which is fibrils. So active regions containing sunspots, which is basically just an area of very strong magnetic field, has an influence over those neighboring spicules. They become bent, they become enlarged, and they follow the magnetic field lines around the sunspot group. So these can be observed as magnetic disturbance around the sunspot in patterns of swirls or whirlpool type effects. And if you look through a H-alpha telescope for the first time, that really is the most striking thing you see. You see these magnetic field lines, this disturbance around these sunspots. It's extremely obvious. And that's what you're looking at. You're looking at fibrils, stretched out spicules, which have become larger, enlarged and thickened, and they etch out those magnetic field lines around the sunspot group. So they're called the fibrils, the dark mottles that follow the magnetic field lines. And individual fibrils can be up to 10,000, maybe 11,000 kilometers in length and about 2,000 kilometers thick. Fibrils can act as a medium to unite regions of polarity, so they can stabilize the sunspot by reaching across it. So here we have, you can see just the swirling effect around there. So we've got our spicules out here, and then the fibrils getting enlarged and bent and etching out that magnetic signature around the sunspot area. And that's got a very good example of that as well. Okay, if we go on to magnetic flux regions then, so a term you may well have heard of, it gets bandied around, nobody seems to know what on earth it is. So what it is deep down in the sun's convection zone, the vertical motion of plasma causes kinks or tangles in the magnetic field lines. Now this causes regions of increased magnetic strength to form, known as flux tubes. And as these flux tubes, they rise, they eventually break through onto the photosphere as small bright points. And that is reflected in the chromosphere as the early development of plage. So as the small tubes, they merge together, they form sort of a larger, more intense structure that starts to stifle convection. And as it stifles convection, that area becomes cooler than the surrounding area and therefore appears darker. And that becomes visible in white light. That's all a sunspot actually is. So in the chromosphere, other features such as arch filaments and Ellerman bombs, they can also accompany developing flux tubes. But if anyone asks you, well, what is a sunspot? Then basically that's what it is. It's just a magnetic appearance on the photosphere. And eventually it becomes a cooler area because of the magnetic intensity and develops in that area. And then that becomes dark. And sometimes, of course, it can just dissipate, particularly at solar minimum. But as we get up to more solar maximum, when the sun is in a more energized state, then those small proto sunspots or pores, they can grow into something absolutely huge. And we'll have a look at those a little bit later on too. Right, an arch filament then, so it's another little feature. So as an active region develops, a unique type of fibril may develop called an arch filament. And that appears as a dark thread that overlies or bisects that neutral line of the active region. They may appear as straight lines or slightly curved features. If seen near the limb, they will appear as a bright emission feature, but bear in mind that these are very low lying. So if you're looking for them near the limb, they're going to be very low, so they're going to be quite difficult to see and visually probably impossible, but it's certainly something for imagers to have a look for within an active region around the limb. It could well be possible to image one. Again, they're quite short-lived. Beautiful image here, just shows everything we've been talking about. So our spicules out here. I've fibrils getting bent around, and then in here, as you can see, we have some of those arch filaments. So not these big ones here, these are sort of proper filaments, but these little ones here, and you can see they do appear as these sort of dark threads, and they are connecting sort of one part of the sunspot group to the other. So they're crossing over that neutral line and helping to stabilize the sunspot as it grows. Now again, Andy, you can recognize this, I think. So you can see in here, we've probably got one of those arch filaments in there. I'm not so sure if that one is, but one of these sort of low-lying ones. I think you've captured one there, Andy. Again, that's just connecting over the neutral line there and just sort of stabilizing that sunspot. Bit of a reconnection event going on there, and a small solar flare as well. Right, Ellerman Bombs, it's one of those snazzy names, but what is it? Well, this is another typical feature associated with an emerging flux region, and even mature or active regions can boast a few Ellerman Bombs. The bright points, very small, diameter about 3 arc seconds or less. They occur low in the chromosphere, about 600 to 1100 kilometers above the surface. The short-lived features, they're just about 5 or 10 minutes, but once they disappear, they can reappear again. So it's worth sort of continuing an observation. They're quite often seen around the edges of sunspots or at the base of spicules and active filaments. They're thought to be the result of magnetic reconnection in the chromosphere, but you probably can say that just about everything that goes on there. So here we have Carl Boron's image. So we have some Ellerman bombs. So you can see it's important to remember we are in the chromosphere here. We are in the solar atmosphere. So you can see these little bright points, sort of minute solar flares basically going on, but not to be confused with a white light feature called an umbral dot. And they appear in similar positions, usually on the edge here of the umbra and penumbra as a bright spot, but again on the photosphere in white light. And that is just an opaqueness. It's just, it can be something that forms a light bridge across the umbra, but it's an opaqueness, and you're looking through that to the sort of hotter regions down below. But entirely different feature to what we're looking at here in the chromosphere with these mini flares or Ellerman bombs. Right, well, that kind of brings us on to prominences and filaments, so we can't ignore them altogether. So we'll just chat about them for a while. So a prominence then is a cloud of gas. It's suspended above the solar surface. They can be thrown up by an ejection from below, or they can condense out of the lower corona, or define a magnetic field that has captured the gas. They are usually relatively cool, about 10,000 degrees, and they can extend for a few tens of thousands of kilometers to hundreds of thousands of kilometers in length. As the magnetic field evolves, and so the shape of the prominence will change. So if you've ever seen an eruptive prominence or one that starts to snake away for hundreds of thousands of kilometers, it's certainly something you won't forget in a hurry. I've not seen an awful lot of them, but when you do capture, it's just sheer luck, of course, but when you do observe something like that, it sticks in the memory for a long time. Absolutely fantastic. So they are viewed as bright emission features extending from the solar limb into the black background of space. They're not limited to sunspot zones, so they can be found sort of in the polar regions. And of course, filaments are the same feature, but they're just observed across the disk of the sun as an absorption feature, rather than around the limb as an emission feature. So they can be active or quiescent. So quiescent is quiet, or they can be extremely active, or they can be eruptive and achieve escape velocity from the sun altogether. So, although these features can occur anywhere in the solar disk, there's a significant connection between them. Active regions and solar flares. An erupting solar flare can disturb an existing prominence or a filament and lead to a very fast moving ejection of plasma, an erupting prominence or an erupting filament. Sometimes the plasma will descend back onto the sun, and occasionally it can lead to an ejection of plasma from the corona called a coronal mass ejection or a CME. Prominences and filaments should be described best you can if you're observing them and if you're imaging or you're drawing them. Often being referred to as hedgerow, arch, multiple arch, jet, pyramid, tree or bush. I described one the other day myself as a church in the steeple, because exactly what it looked like. Somebody else described one as an upside down wine glass. So you can be creative if you wish. There's no actual code as to describing them, but just try to do the best you can. Hedgerow is I think I've got one here. Oh, that's you can see there, there's an eruption there, a little piece of plasma there being ejected. But this is the more sort of stable type hedgerow prominence, and a typical example of descending or quiescent type of prominence, where plasma is flowing back down to the surface. Occasionally there is a flow between the elements, which is described as interactive and comprised of a horizontal flow of knots and streamers between the elements. So again, these are things all to look out for when you're doing an observation, and also to make notes of. The two ends of the hedgerow prominence are usually magnetically anchored to the solar surface, producing a stable and quiet feature. But if one end breaks free of its anchor, it's usually a sign it's about to erupt. And I think I have one in a moment, but there's just a filament, and that's very similar to the hedgerow prominence you've seen, with all those barbs there anchoring it all onto the chromosphere. Now, this is differential rotation. This is what's called a polar crown. So differential rotation, because the sun rotates slower towards the poles than it does at the equator. And that can cause a lengthening of filaments as they drift towards the poles. And some arrive at higher latitudes and join others already present and form a polar crown. Of course, it can occur well, at the south or indeed at the north. So again, it's just another feature to look out for and to put in your observing logs. You might sort of not really notice that you've got a chain of filaments there, but it is an actual feature that can occur when they all kind of gather there. So that is known as the polar crown. So again, it's just something for your log and to make notes of. This is an ascending type of prominence, and it probably be erupting in some sort of forceful ejection. As you can see there, a rather beautiful feature with the plasma drifting off into space. Most prominences that achieve a height in excess of 50,000 kilometers erupt within a day or two, and passing shock waves from a solar flare known as the Morton wave can cause a rapid oscillation of the prominence or the filament, leading to eruption. And there's one of Andy's captures, and you can see just the anchor at the northern end has for some reason become disturbed and broken, and that has fired off a huge amount of plasma. So rather beautiful movie there, Andy. Well done, fabulous. Of course, it's speeded up, tremendously. So I mean, if you're at the telescope observing that, you don't actually see it move, although you think you do, because if you're looking away to sketch for a few moments, then you look back, you will see structural change. So when you've got sort of a sort of dynamic eruption like that going on, it's a lot of structural change going on, and it's moving pretty quickly, even in real time. So you'll see structural change over a matter of minutes, and certainly a huge amount of change over like half an hour or so. And here's quite another one. I think it's graced the handbook back in, I think, 2011 or something like that, 2012, somewhere around there. Can't remember now. So absolutely stunning image from Andy, brilliant. And there we've got a huge bubble of plasma has erupted from the sun. It's joined a magnetic rope. These magnetic ropes get filled with plasma, and when they do, they burst, and that's what causes this massive eruption, and all the plasma just has enough force to escape the sun's gravity, and away it goes into space. You can see a different image there, where a few minutes more down the line, and again another one here when it's dissipating away out into space. So it's really so the attraction of the sun. There's just really, excuse me a moment. It's just such an active body. There's just so much going on. And I think that's its huge attraction for any imager or for any observer, is you never quite know what you're going to see. And even if it's been quite mundane and boring for a few days, then when you put eye into telescope, there's just anything can happen, quite frankly, particularly in H-alpha, in the chromosphere. And you can just be extremely lucky and see a coronal mass ejection or an eruptive prominence or a solar flare or whatever. So, you know, it's just, if you get a lovely sunny day like I have today, and you have the time and inclination, and get out there at 7 in the morning and still there at 7 at night, it's amazing what you might record during that time. Another feature then, post-flare, pretty much as it sounds. So after you've got a solar flare, you get this quite distinctive feature occurs. So these follow the outburst of a flare. Sometimes the loop is open at the top, and that leads to a feature called coronal rain. And you can see that is exactly what we've got here. So this is this plasma just dropping straight back down onto the chromosphere. So that's a feature called coronal rain. Consists of faint streams of plasma and knots of gas pouring back from the gap onto the chromosphere. So there's just another different image. You can see how distinctive it is, a post-flare loop, so you can't really mistake it for anything else. Got a rather nice movie here from Alexandra Hart, and it's this one here. I think you're looking there at a post-flare loop, edge on, so you can just see all those streamers coming down. So I think that's what she's captured there. Here you can see a lovely example of a descending prominence. So you can see why it's called that. So you've got all this plasma caught in this magnetic field line up here, but then it's just starting to stream back down onto the chromosphere. Beautiful, beautiful image. Right, so we have ascending prominences and descending prominences. So we've had a look at that. Ascending prominences and filaments are those that erupt in a forceful projection, and a spray prominence is a good example of that. A filament associated with an active region usually erupts quickly, whilst those associated with quiet regions erupt more slowly. So eruptions are caused by solar flares or other magnetic disruptions, such as a reconnection or a realignment of a magnetic field line. The rapid disappearance of a filament is sometimes called a disparition brusque, when several billion tons of matter can be ejected from the sun in a coronal mass ejection. And I have to show you this. I thought it's the Andy Davies show. This is a very interesting thing that is caught here. If you can just see this, play it a few times, this very dark burst there. Just see it just go there. Actually, again, there it goes. That dark burst there. Now, historically, observers have from time to time drawn these dark prominences, which has been a bit of a mystery. So prominence is a bright emission feature, so why are people drawing dark ones? So could this be what people have actually been viewing, just what they've seen? It could well be a cooler filament that's erupting in the foreground, so against the brighter backdrop of the prominence, or it could be associated with the prominence itself. So it could be an eruption from the lower and therefore cooler part of the chromosphere, and just making that eruption appear dark against the main prominence. I'm going to go for the latter. I think it is associated with that, but I've no real justification for that. It's just my thoughts. Interesting to hear what you think about it, Andy. But I must say that is one heck of a capture. Absolutely cracking. Congratulations. Right, a surge, then that is a controlled or a relatively continuous expulsion of material, usually after a solar flare. A surge will often burst outwards at any angle to a height of several thousand kilometers and fall back again, having lost inertia, causing a kind of splashing effect. The velocity of a surge is therefore less than the escape velocity for the sun at 600 kilometers per second. They appear as dark, gradually becoming transparent until they disappear. But of course, from the scene at the solar limb, it appears as a bright jet or a spike in emission, which rapidly grows and falls back or disappears. So it's just something else for you to look out for. And it's really just a matter of not drawing things or taking images and thinking, that's a nice drawing, that's a nice image, and filing it away. But once you've processed your image or you've finished your drawing, it is to look very carefully again, look back at it and see, what have I actually got? And sort of look at all these different types of phenomena that exist within the chromosphere and say, well, can I analyze that? Perhaps I've actually captured something a little unique or a little rare. And then, of course, please let me know if you have. So do analyze your images and your observations rather than just doing them. So that kind of brings you on to solar flares, which is the exciting part of solar observing. So a solar flare, then, it's a sudden and extreme release of stored up energy, primarily found within the magnetic field of an active region. Energy is released as a consequence of reconnection between magnetic field lines. Reconnection or realignment generates massive electrical flows which heat the surrounding plasma to millions of degrees, which is powerfully accelerated away from the sun. The bulk of flare energy release is in wavelengths beyond this in the visible spectrum. So that's why we don't see it. It's in other wavelengths beyond visible. But sometimes, of course, you can see them in calcium K-line, and sometimes you can see them in white light. And that's something we'll come back to in a moment. So a typical flare starts as a rapid brightening or a series of bright spots, usually associated with a sunspot group, but not exclusively. So if it's not associated with a sunspot group, we call it a Hyder-Flare. So there is a period of rapid growth to maximum brightness, that's called the peak, and then it's followed by a gradual decline in intensity. So let's have a look at some. So Andy, you can sit back and admire some of your work here. So there's a nice M-class flare by Andy there. So you can see we've got a bit of an ejection there, of course, of plasma, that dark thing coming out there. That's an ejection of plasma out of this solar flare. So not only dealing with brightness, but also dealing with the extent of the flare as well, and that's a pretty extensive one. So that's a little cracker back from 2012. I particularly like this one because we're kind of looking straight at that. We're straight down at it, and you can see there the flash of the flare, the intensities, and of course that dark ejection of material coming out as well. You might have seen this one on Space Weather just a few weeks ago. And the interesting thing about this one is we've got this ejection of plasma coming out of this flare, but also it's a C-class flare. I'll go through classifications in a moment, but C-class is much weaker than an M-class flare. So it just goes to show you don't have to have the strongest flares in order to get an ejection of material. And this one was an X-class flare, so a real nice little cracker there, as you can see sort of the brightness and intensity of that. And he didn't do this one, this is the SDO. So we've got a fantastic X-class flare there, and again you can see the flash of it and the release of material. So got the very highly charged particles, of course, are traveling at the speed of light, so they're coming out. But this material, this plasma release, is traveling relatively slowly. And so that's going to take some time before it reaches the Earth. And if it's down this sort of central area, as this is, then that's pretty much going to be earthbound. So that's probably going to hit us, depending on what speed it's traveling at, of course, probably in about 2 days or thereabouts, and hopefully cause a nice aurora. So not every flare results in a coronal mass ejection or the release of material, but an awful lot do. Back to Andy again. Now, I like this one because you can see there's a filament there. This is what's called ribbon flare. So we have the flares occurring right the way down both sides of that filament, and it's causing the filament to erupt. And you can see it being ejected there, but it doesn't achieve escape velocity, and it's pulled back down again. And that's just another view of another flare going as that particular active region disappeared around the western limb, and some very nice filaments there. So you can see that would be a lovely arch prominence of that being on the limb. Right, so 2192 released an awful lot of solar flares, and it released the highest category of solar flare, which is X class. And you can see there we have a number of them listed, and one was X6.7, which I think was probably the highest or the strongest solar flare of that particular solar cycle. I could be wrong about that, but I can't recall one that's stronger. And that was a sunspot group in white light that released all those solar flares. So if you're thinking, well, what kind of sunspot group do I need to observe in order to see a solar flare? Then this is a really good example of it. And you can see within this, we can practically imagine a solar rotation. You know that sunspot, its magnetic fields are rotating around. And when you've got this kind of rotation going on within a sunspot group, it's really, really messy. And when it's messy like that, you're going to get tangled magnetic field lines. And when that happens, they're going to disconnect and reconnect, and that is going to give you a series of solar flares. So that's the kind of sunspot to look out for. So I'd ask you just kind of memorize that look of that sunspot, because we'll kind of come back to similar things a couple of times in a moment or two. So yeah, okay, coronal mass ejection, as I was saying earlier, it's this huge bubble of plasma. So you've got plasma fills these magnetic ropes, and then they burst basically, and that's what a coronal mass ejection is. Something here from Soho. So you can see that that is the size of the sun. This is the coronagraph, and the Earth is probably a pixel or maybe even less than a pixel. So if you can imagine the size of that, and then look at this huge bubble of plasma coming out here. So when that is earthbound, it completely bathes our planets and a whole lot more. So you can see why we get aurora happening when that comes our way. So these are the type of sunspot groups to look out for. So mature sunspot groups, or the Macintosh classification of D, E and F, they are notorious for flare production. So also growth or rotation within a sunspot group can indicate a twisting and distorting of the neutral line, and that can indicate likely flare emergence. Most larger flares appear about 2 years after sunspot maximum and tend to occur as the group is developing rather than during its decay. So there we have a D-class group, so a leader and a follower, maybe some stuff in between, as you can see there. But it's less than 10 degrees in solar longitude. So E and F, they are longer than that. They're 10 to 15, sometimes exceeding 15 degrees for F-type. And they're also complex. So as you can see, you have a leader, and you might have several penumbral middle ones as well as a follower. So if we go on to look then at the category of flares, there's two main types of classification. I'm not going to dwell on it too long, but just suffice to say this is the H-alpha classification, which there are two types. So you can measure your solar flare in square degrees. So subflare up to category 4, so an area more than 25 square degrees, or you can do it in millions of solar hemisphere, which is this one here. So that's called importance 0 to 4, and it's also a qualifier of faint, normal or bright. So if it was a tiny flare, it would be 0F, put it on there, 0F, so that's the smallest type, and faint. And if it was a really big flare, then importance would be 4, exceeding 1200 millions of solar hemisphere, and your classification of B for brilliant. But I think you probably recognize this one better. It's the Americans invented for the X-ray GO satellite. So a lot of flares are categorized as A, B, C, M and X. Don't ask me why it's A, B, C and then M and X. I've no idea. Each category has subcategories of 1 to 9. So you have M1 is 10 times more powerful than C1, and X1 10 times more powerful than M1. X classification is open-ended, so that can go all the way up to whatever you like. And I think the Carrington sunspot was estimated to be something like X46 or somewhere around there. So C classes are good. M class is getting exciting, and X class, that's really brilliant. So yeah, that's the holy grail. I've seen many of a C and M class, but I've never actually seen an X class. Again, it's luck being at the telescope at the right time. So yeah, back in 2003, we had a solar flare. It was an X45 flare. They initially thought it was X28, but it flooded out the chip on the camera to such an extent, and when they sort of went back and analysed it, they found it was actually an X45. And here it was captured. So you can see how fantastically bright it was. Of course, it's Earth-facing as well. So yeah, I think that did give us some pretty good aurora, if I remember right at the time. And that's what it looked like. Now, a reason I asked you to remember what that other one looked like, they're very similar. You can see that sort of sunspot rotation going on there. So there's twisted and tangled magnetic fields. So those are definitely the kind of sunspots to look out for. If you see that signature, then keep an eye on it, 24/7. Some of you might be able to remember back in 1989, it was a huge sunspot, and that caused havoc in Canada and caused their grid to black out in Quebec. And that's what it looked like. So there we have it again. It's exactly the same as the others. That's really extensive. But you can see it's how it's got that, again, that rotation feature in it and all those twisted and distorted magnetic fields associated with it. And that lashed off a fantastic flare. Right, so let's briefly look at Hyder-Flares. We have mentioned them. So this is the term used for a flare that occurs not in association with a sunspot group or an active region. It often occurs when a filament lifts and visually appears as a series of twisted bright blobs on both sides of the filament, or as a ribbon flare, and we saw that in Andy's movie, that ribbon flare. So this is a slower event than an active region flare, and the peak can last up to an hour before slowly fading away. The intensity is usually less than an active region flare, but it can be spread out over a greater area. These are not yet fully understood, but are thought to be produced by a reconnection event around a dissipating filament. Now, I'm going to give you a really rare event now. In the 15 years I've been director of the section, I don't know how many thousands of images I've received, but regards a Morton wave, I've received 2 images. So if you're looking for a project images, then this is certainly one for you. Probably more around sunspot maximum when we get really strong and energetic solar flares. So a Morton wave then is a flare-related feature, along with post-flare loop surges and spray prominences that we've already looked at. It's basically a shock wave visible in the chromosphere resulting from a large or intense solar flare. So I hope you can see it. It's just this kind of darkness here. You can just see around there, and it carries on there. So it's kind of a solar tsunami spreading out within the chromosphere. Very difficult. I don't know if you can see it visually. I don't think so. Very difficult, certainly, to image. And that is a cracker by Nick House. So if you want a project, have a go at that one. The shock wave appears as a single arc emerging from the flaring active region and travels about 500 to 1500 kilometers per second. If a magnetic barrier is encountered, such as another active region, the wave is disruptive. And sometimes the wave encounters a filament, causing it to blink out of visibility as the wave passes underneath it. And this is called a winking filament. So the motion may well cause the filament to lift or to erupt, and such features are difficult to observe as they are quite diffuse and low contrast. Again, that's a pretty rare event, a winking filament, something I've never seen. But again, it's something for an imager to have a look at. Maybe someone that does movie or time lapse may well, capture something like that on analysis of their work afterwards. So we said about white light flares, so I'm just finishing now. So we'll just consider white light flares before we do so. So white light flares, and these flares, they are so intense that they become visible in wavelengths other than H alpha, and they become visible in the photosphere as a white light feature. The peak may only be visible for a short time, perhaps 5 or 10 minutes. And so again, luck and good fortune plays a huge part in observing this sort of feature. A truly bright white light flare is rare, but the lesser type on the cusp of visibility may be observed more often, particularly, again, if you're imaging. Again, the sunspot groups D, E, and F are those to target. with subgroups Ki or Kc, and that just means lots of stuff between the leader and the follower, basically. So we've got lots of tiny sunspots or little detached parts of sunspot penumbra. Then that's a Ki. Kc is a sunspot with lots of small sunspots with penumbra in between the leader and the follower. So pay close attention to irregular or detached penumbra within the sunspot group and areas of clustered sunspots between the leader and the follower. Direct viewing using a solar filter also increases your chances on the brightest would be seen with projection. That's certainly something I've discovered, especially as you start to get a wee bit older as well. You don't see things so well when you project, but it's good obviously for the public. But if you're doing serious solar observing, then I would recommend that you do get a proper solar filter and do direct observation. You see a lot more detail. Sometimes a mild blue eyepiece filter may also help with the contrast. I think that's very much based on your own eyesight. That's the Carrington sunspot back in 1859, and again you'll see from that drawing again exactly the same as we've seen on those two images, that rotation in the sunspot. So exactly the same thing. So magnetic field lines connecting and reconnecting, disconnecting, and all the rest of it, producing huge solar flares from this kind of rotating sunspot. Back in March 2015, we had this sunspot that it released a solar flare, a white light solar flare, or should I say a solar flare that was visible in white light on that particular day. I think it was only M-class though that it released. That isn't it happening. That was the sunspot on the same day, but unfortunately I didn't have an image of it actually flaring on that day to show you. But it just goes to show that you don't have to maybe have the strongest X-class sunspots going across to actually get a white light flare. So again, for images, you know, just have a look at M-class flares as well, and just see maybe if you've got, you know, a white light flare just on that cusp of visibility, just creeping there into white light spectrum. It continued. I think this is a sequence by Andy again, and you can see this sunspot was just very active, and you can see at the following day and subsequent days it was constantly flaring and producing all sorts of interesting stuff. And again, a little movie there just showing you another flare going off and injection of material there. So a nice little sequence. And that's what it looked like in white light. So not quite as complex as the others that we've looked at, but all the same, it's still got that messy signature. It's still got these sort of bits of penumbra and little bits of sunspot umbrae hanging about. It's not clean cut. It's not a nice sort of leader follower type sunspot. It looks pretty messy, particularly you can see all this sort of dark area across here, you know, and here. So when you see that, it's a bit unconventional. So again, it's just maybe a pointer to sort of keep an eye on groups that look like that, keep the camera on it and see what you can come up. And I think that brings me nicely to the conclusion. So if you've got any questions, I'll do my very best to answer them. And my thanks to Andy for all your wonderful images.
Right, ladies and gentlemen, thanks, Lyn. And I'm going to ask our audience to wave a hand at me and announce them. Now, as I've said, I'm a novice at this hosting. Paul usually does this, so this is my first go. So bear with me. So wave your hand and I'll look. Anybody got a question? Wave your hand. John Leach, if you'd like to unmute yourself.
Yep. Hi, Lyn. Lyn, that was absolutely fascinating.
Oh, thank you.
I've only just started in astronomy in the last year, so I'm making up for lost time. So I've been trying to look, I've been looking at the moon, I've been looking at nebula, and now I've just in this last 2 weeks started looking at the sun.
Good.
And I fear that your talk will cost me some money.
Yes.
But,
Well.
but I'll be quite happy to purchase a proper solar scope. Thank you very much indeed, Lyn.
Well, that's great. Well, you know, you've got Mick in your society, so he's ideal for getting you sorted out. So all the advice.
Ready?
Yes.
And Andy.
And Andy, of course.
Just one for you. Somebody asked what size telescope the rather large eruption that I filmed was done with a standard unmodified PST,
Good grief.
which about 450 quid, but I bought it, I think, in 2005, and I'm still using it.
Something to do with the talent of the imager, I think, Andy.
I think that one went down to location, and location over in Spain.
Yeah, he certainly produced some very fine work from there.
Anybody else waving a hand? Catherine, like to unmute yourself?
When processing these images, would you recommend using sharpening with like a high pass filter, or would you recommend using deconvolution?
Andy, answer that one.
What I've always done is they're all video images that are originally processed in registacks, but now I tend to use auto stack it. But I use wavelets in registacks to sharpen them. But you've got to be very careful because it's very easy to over sharpen. And remember, with the sun, it's something that's gas. It's not a solid feature like the moon. So just be a bit wary of it.
Thank you.
I've never tried deconvolution. It's because if it's something I can't spell, I tend to avoid it.
Thank you.
Anybody else?
Just out of interest, there's magnetic field strength within sunspot umbra is something that scientists can measure. Don't ask me how they do that, but they do. It has been declining over quite a long period. And there was some sort of thought that it might well lead to another Maunder minimum type event, and that could happen around 2022. Well, that's been amended now, and the most recent information is, I think it's, if I can find a piece of paper, 2034, I think. So it is continuing to decline. So around about mid-2030s anyway, they reckon that if it continues to decline as it is, then we could well hit another Maunder minimum type event. So that would be great, because as that event occurred in 1645 to 1715, I mean, obviously we didn't have the technology we have now, satellites, we couldn't measure what was happening to the sun. So I rather hope it does happen. It'd be a very boring time to be a solar section director, but I won't be by then anyway. But we'll be able to look and see what the condition of the sun, what's it look like as it goes into one of these long sort of quiet sleep processes, because we don't know what causes it to do that, and we don't know what causes it to come back out to the side. So scientifically it would be very interesting if that does happen. I hope, if I'm still here.
If there is one, Lynn, and there are lots and lots and lots of amateur solar astronomers, so I think I'm going to pre-name it as a Maungy minimum, because I will be very, very fed up if I'm still about at that time.
Exactly. And there's also a couple, well, there's many predictions about this solar cycle that of course it's now ramping up quite nicely, but there's lots of predictions about that as well. And we've got two pieces of work which I have here, and one to do with the sort of the transition, you know, how the magnetic cycle is really 22 years long. Well, that transition, if it's quite rapid, it means we're going to get a really strong cycle. If it's very slow, then we'll get a very weak cycle. Well, apparently they have said that it was a very rapid transition this time around, and so they're predicting that we're going to get a very strong cycle coming up, so a really, really strong cycle, this one. And they're also predicting that we should get sunspots around about in excess of 40 degrees north or south. So if you're an observer, please look out for that. I haven't seen any evidence of that really. There was a sunspot group which nearly formed a few weeks ago at that high latitude, but didn't. So there's no real evidence that that's occurring, but I would like observations, please, of any high latitude sunspots you happen to find to sort of back that up. And then there's another piece of work that looked at the asymmetry of sunspots on the northern hemisphere to the southern hemisphere, and they've worked out and concluded from their work that this cycle will be one of the very weakest cycles on record. So it just goes to show that the professionals haven't got a clue either.
Just a comment, actually more for Andy. You're talking about that shock wave on the sun. And I seem to recall, didn't you record one a year or two ago, Andy?
I got one in 2012 with a PST, and you can see a very, very definite depression. I've caught another one since then that it seems to run along the surface and also goes up through a filament as well. But both of which, I think they're both on the front page of my website. So I'm there.
I'll have a look. You probably sent them to me anyway.
So has anybody got any other questions? Wave your hand.
There is a really significant one that was filmed from the Global Oscillations Network survey, GONG survey, from an X6 class flare. And I've got a video of that somewhere that whether I could find it, it's an enormous, and it goes right across the whole surface of the sun.
Well, if you can find it, Andy, do send it to me. That would enhance my talk a little more.
And them GONG telescopes are not very big, are they? They're not high resolution. So anybody with a decent solar telescope that is able to put the time in for time lapse, because it's the time lapse stuff that picks stuff out like monitoring waves. They're very good. I'll fish it out and send it to you, Lyn.
Thank you. Excellent.
Catherine, you've got a question.
I've always got a question. People mentioned the 11-year cycle, but doesn't the polarity vary, a change of every cycle? So why isn't it known as a 22-year cycle?
Yeah, well, it's just, we just call it 11-year cycle. You're quite right. It's if you've got a sort of positive sunspot leading in the northern hemisphere, then it'll swap round after 11 years, but then it'll swap back again. So to get the sun back to its magnetic configuration it started at, then it's a 22-year cycle. But you can plot sunspots over the 11-year cycles. It's you can say either it's 11 or 22. So who's right, chicken or the egg? It's conventional to say 11, but you sort of add a postscript that it's really 22.
Thank you.
Have we any more questions? Michael McNichols, can you unmute yourself?
You mentioned about possibly going into another Maunder minimum, with cycle getting weaker.
Yeah.
But could it just not be we're reaching bottom at Gleisberg cycle?
Oh, go on. Tell me some more.
Every 8 to 10 cycles, it starts off weak, reaches a peak, and then it goes down again, doesn't it?
Well, who knows? Who knows, Andy? I mean, I'm only telling you what the professionals, tell me. Sort of might make rather. It's just, a piece of work that they've done. They're looking at these sunspot umbra and saying that they're declining over time. So yeah, there are all sorts of cycles within cycles going on. But you've just got to look at that work, and they're going to, they say that there's going to be a Maunder minimum based on that piece of work. We, in the solar section, we don't predict. I mean, I'm just telling you what the professionals are predicting, but we don't go into that sort of thing. What we do is to examine things on a daily basis and tell you what happened today, what happened yesterday, and over length of time, we'll tell you what did happen. So that's pretty safe, really. So, I'll come back and tell you what did happen in 20 years' time, maybe. But, that's not a field of work that I'm in, so I can't really comment in detail on that.
Okay, anybody else? I think we've run out of questions. So would everybody like to put their hands together and thank Lyn for such an excellent talk? Very interesting, and more about the sun now than we did.
Thank you. I'm going to exit now and leave you to the rest of your meeting, but thank you for the invitation. It's been lovely seeing you all and hearing those great accents.
Okay, thanks a lot.
Bye.
Bye-bye.